And hello guys, welcome back to our radiation heat transfer learning journal. In the last video we were talking about the heat radiation network, electrical network analogy. So now we want to have the case of, let's say we have three surfaces, and then how are we going to solve this problem? Okay, so we have this surface 1, 2 and 3. So there's J1, J2 and J3. So just J1, J2, J3. Okay, so now I want to draw the equivalent black body. So this EB1 and this equivalent black body will be EB2. Okay, and remember the blue colored resistance. This resistance is this surface resistance. Okay, so again same thing, I have EB3 here, and the center, of course, we have the view factors and everything. This is the space resistance, if I'm not wrong. Space resistance that is due to the view factor, which is 1 over A into 1 over A1 F1 to 2. Okay, so that's 1 over A3 F3 to 2. Okay, let's draw it properly one more time. Hopefully that's okay. This is 1 over A2 F2 to 1, and last one 1 over A1 F1 to 3. Of course, you can use the reciprocity rule to switch the resistances around. Reciprocity rule still applies here. Okay, so though with this kind of a delta network, there's a delta because it's a triangle, it can get kind of tricky to start solving these problems. So what is usually used, according to my professor, he taught me before, this is called the delta Y resistor network, delta Y transform. So what the delta Y transform means is that you can convert this kind of triangular network into something like this: R1, R2 and R3. Okay, so this is Khan Academy, so I probably want to put that link in the description. So I'm just going to copy and paste what this is about. So basically I can transform this into this, which is probably much simpler to solve, so I don't have to think about all the parallels and everything. So what is this? What are the appropriate resistances? They are written here. Okay, so the denominator is RA, RB and RC, which is RA, B and C. So what is R1? R1, you can take a look, RB and RC. Well, RB and RC, they are connected to the X terminal, so these two multiplied together over the sum of all the three. Same thing, R3 is equals to RA times RB over the sum of all the three resistances. So RA, RB over RA, RB and RC. RA times RB over RA plus RB plus RC. Yep. So same for R2 is RA times RC over the sum of the three resistances. So we can change this. Okay. Solution, we can of course change this into an equivalent network, which I will use a red color. Alright, I'm going to use a red color and I'm going to draw as such. Okay, so that's R3, R1 and R2. Okay, so do note that this R3 is referring to this one you see here. These two come together in one diagram from this website. And this one is a different diagram. So, okay, so what is R1? That's equals to the sum of all three. Sum of all three, what do we call that? Space resistances. So, maybe I'll just write that down, since I can copy and paste later on. 1 over A1 F1 to 2. Alright. Or A1 F1 to 3. I mean, the reciprocity rule does give you a little bit of flexibility. 1 over A2 F2 to, what is it? 2 to 1. So that's the second resistance. The third resistance is 1 over A3 F2 to 3, right? F3 to 2, which is this one. A1 A3 F3 to 2. Alright, so what is R3? On top, you should have these two. 3 to 2 and 1 to 3. So whatever has to do with 3, if you see a number 3 in the, alright, sorry, this should be R3. Whatever you see with the 3 in the view factor, that will be what you need to put on top, because that touches number 3. So likewise, R2 equals to all of this. So the denominator is the same. Now just need to replace it with this. Okay. Why am I doing that? Because there's a pattern there. So wherever you see R3 going to the third node, you will see anything with this the view factor with a 3 in the any view factor with a number 3 there, that will be what you place in the numerator. Similar case for R2 and now R1 as well. So I'll switch this around and it'll be as such. R1, R2 and R3 are as follows. Okay, hope the concept is simple. And then now what do you do? Okay, so we have EB3 and then a central like resistance there. So let's just put, let's say JC, like a central radiosity or potential of some sort. Okay, so what does it mean? So Q3, for example, Q3 is equals to what is this? The potential difference, which is JC minus EB3. Then you'll have the space resistance added to, what is the surface resistance there? Surface resistance is 1 minus epsilon over epsilon times the area. So 1 minus R epsilon 3 divided by A3 var epsilon 3. Okay. So likewise, Q2 equals to whatever this is, except now we just replace the 3's with 2's. And likewise, Q1 is the same. Okay, so we basically have all these view factors done, assuming of course we know the view factors. Okay, that will be coming from some table. Sorry, there should be a Q1 here. So now we have basically 4 equations and 3 unknowns. So we'll kind of need one more equation to kind of set everything in its place. So what is that equation? Yeah, hold on. Yeah, so what's that equation? Okay, for example, we can include J2 in there. Q1 or Q2, for example. If we are to include J2, we can do it in this way. So JC minus J2 over R2, and that is equal also to, so this is 4 equations with 5 unknowns. So Q2 also equals to J2 minus EB2 divided by the surface resistance, which is this. Now what are the unknowns? Unknowns, so J2, JC, Q1, Q2, and Q3. We assume those are unknown. We assume all the resistances are known. So we have 5 equations, 5 unknowns. At least in theory, this system of equations should be solvable. So what we can do is basically eliminate J2 out of the picture, or eliminate Q2. Okay, so yeah, so basically we can solve these 3 equations, this 3 system of equations first. 1, 2, and 3 here. Okay, so we can just do an elimination of Q2 first. So I'm going to combine the last equation with the second last equation. That will eliminate Q2, and then I will also combine the second equation with the first equation. That eliminates Q2. So this is a simultaneous system of 2 equations with 2 unknowns, which is pretty, now it's more or less straightforward to solve. So let's make JC the subject, since we want to find out JC, because we want to find out JC because JC will help us to determine all the other heat flux, right? So let's make J2 the subject here. Okay, make J2 the subject so as to eliminate it. So let's go. So this J2 minus EB2 will be equals to whatever this is, and then you divide it by R2. Yes, and you have JC minus J2 here. Okay, so I will want to multiply that in. Okay, I'll cut this out and paste it here. Okay, then I want to move it over J2, 1 plus whatever this junk is here, equals to, I'm going to shift this baby over, I'm going to plus this over here. Alright, so we'll have an expression for J2 very quickly. So we'll just have all of this on top and all of this at the bottom. So with Word, you can do all these copy and paste tricks pretty quickly, which is pretty convenient. And now we can substitute this back into this equation. Substitute back to find JC. So with J2, we can just copy and paste everything here, and it's gonna get rather messy and pretty unsightly, but unfortunately that's what we have to live with. Yeah, let's see whether we can make this thing slightly neater. Okay, I'm gonna bring this down, and I'm going to basically I'm multiplying both top and bottom by this factor, so I'm just gonna do it as such. Okay, so now we want to make JC the subject. I'm gonna make this baby the subject. Okay, so it's gonna get very messy, so let's do this. Okay, let's do K1 equals to whatever this is at the what this junk is at the bottom. K2 equals to this. K3 equals to this, and then K4 is equals to all of that. Alright, I don't want to do any cancellation of any sort. It will get pretty messy. And what this does, and we look at a neater equation. Okay, so again, K1 is at the bottom here, K2 over here. Oops, I mean K2 is here, K3 is here, and then K4 is at the bottom. So now, well, with this, it should make it easier to manipulate, especially on paper, if you are doing it on paper. So I'll first multiply both sides by K1. So I'll just do this, and yeah, I'll have K1 by K4 on top, and I'll have this whole thing here. Yep, K1 by K4. Okay, and let's multiply that in 1, 2, 3, and I'll cancel this out. Next thing is let's bring this EB2 over, and let's bring this JC factor over. Alright, so what we have is a JC 1 minus something. So we just factorize JC out, and we can factorize EB2 out as well. 1 here, and divide here. So what we are left with is the JC equals to EB2 times all of this divided by all of this, and then we can write where K1, K2, K3, and K4 are as follows. Okay, so that's where we find our JC. Once we find JC, we can easily find our Qs. Alright, Q1, Q2, and Q3. With JC found, we can substitute back into Q1, Q2, and Q3. So you just substitute whatever relation for JC in here, and then you'll have the heat flow from each of these nodes. Okay, so yeah, this is how the radiation resistance network kind of works. If we were to follow the circuit analogy exactly, this is how we would come to find our answer. Alright, so it's a lot of manipulations, copy and paste. Though of course, yeah, it can get pretty messy, and you should know the this only applies to diffuse Bray boundaries without any kind of external radiation in. And of course, you must know the surface resistance and the view factors, otherwise this analysis kind of becomes a bit useless. But yeah, this is just to give a flavor of this electrical network analogy. And the thing is, obviously, as the number of surfaces increases or the system gets more and more complex, then even the electrical network analogy kind of doesn't become useful, because if the electrical network becomes so complex that you can't solve it on pencil, paper and pen, or even on this using Word document or something, then maybe you're better off writing a computer software to solve it. But this is how you would solve it if you were to use the electrical network. So yeah, thanks for watching. I'll see you guys next time. Then probably we can move beyond electrical network. Now I'm going to skip this. Hopefully we can start looking at the radiation transport equation, or the radiative transfer equation for participating media. Alright, thanks for watching. I'll see you guys again.